My talk today is actually deviate from my normal talks, which was more on tropical dynamics and also on winter monsoon and everything. And this is a new direction, but I think it's an interesting one. On the the title says it all. Some background is that in 2008, or could be 2009, plus minus 1 year, 2008, there was a Typhoon Morakot, which made worldwide news that caused a lot of damage and a loss of life in Taiwan. And it produced a record-breaking rainfall. But record-breaking rainfall is not just that one, but occurs in a number of tropical typhoons that hit Taiwan since this century, since 2000, actually, and more. So therefore, that was also the time, like a few years after Al Gore's movie on Inconvenient Truth, right? And wins Nobel Prize on global warming. Then you remember you watched the movie. There's this Hurricane Katrina that wiped out New Orleans, and then all these warning and alarms on global warming and like the end of the universe or the Earth is forthcoming. So the same kind of atmosphere dominates Taiwan because of this Typhoon Morakot, which is never before we have such flood and damage. Typhoon Morakot happens to, there are two consequences that are not scientific. One was that it was the first time ever in Taiwan the government was replaced. The prime minister fired. Okay, maybe because he didn't do enough to save people or whatever. But anyhow, that was one event, and the other event was all the newspapers attacked the Central Weather Bureau. Their delegation to visit here tomorrow. Okay, and the government has this special inspector or investigation officer. Not officers, there's committee members who come down to investigate how come you miss the forecast so much, so so much flood. And then there were all people like my colleagues, scientists, PhDs, professors. They were saying, "Oh, this is all global warming," and the weather forecast did not take into consideration the fact that global warming is going to cause more to allow more water vapor in the atmosphere. Therefore, they should have increased their model forecast. Like the model forecast says 100, they should say, "Oh, because of warming, so there will be 200," something like that. So because they didn't do that, so the government, this high-level investigation committee members are descending into weather service, and they do everything in the public, in the newspaper. Every time it's a news conference, we're going to find out that they're not doing their job, and we're going to punish the director and so forth. So these two things were happening in that time. Okay, and so that's the background of this talk. And this talk actually consists of two pieces of work working with different people. But the first one is extreme rainfall over the China area. I call it China monsoon. I can't quite call it East Asian monsoon because we didn't have Korean and Japanese weather in there. But it's sort of 80% of the East Asian monsoon, extreme rainfall. And the second part, the main part, is related to this. So the first one is tropical cyclone China summer monsoon extreme rainfall, which is defined as the 90th percentile. This data used is 58 to 2010, so it's still 58 years, more than half a century. And the second part is on this Taiwan tropical cyclone rainfall intensity changes for 50 years starting 61. The daily rainfall data is available only since 61. And we have recently extended, I think, to 2014. 2013, 2014 is the same because there was no typhoon 2014. So I should put 2014, make it look like longer. Okay, everybody knows this. These Taiwan high-level committee members were told by the professors that global warming causes increased water vapor capacity, and therefore there will be increase in rain intensity. More rain can fall in a given time, and more extreme rainfall. Okay. That's a theory. Now, I'll just go one by one. There were model simulations shows that extreme rainfall has an increasing trend in the last 50 or years or so over the northern hemisphere land area. And this is observed in like European, Western Europe and North America, but very confusing over our region, over the Asian monsoon region, okay, both India and East Asia. And meanwhile, we have this other thing I just mentioned. There's a very large increasing trend of extreme rainfall in Taiwan since 1998. And this attribution to global warming is a subject of ongoing debate. I already mentioned that this Typhoon Moraga caused a change of government. All right, here is a slide, not the most up-to-date, but I think still valid paper. Basically shows the agreement or disagreement between model forecast extreme rainfall trend. Or I should say model, not forecast, model produce extreme rainfall trend and observed rainfall trend in the last half century of 20th century, 1951 to 99. And if we look at this is anthropogenetic model says there's increasing trend over here, increasing trend over there. It's all over the northern hemisphere land area. There are two definitions of extreme rainfall looking at 1 day maximum or 5 day, okay, it's the same. And if you include the natural causes, the model says, again, there's increasing trend here and here, still basically increasing here. So this is the man-made increasing. But observation, there's good agreement over North America, it's blue versus blue. And over European regions, blue versus blue. But over the Asian monsoon region, it's confusing. It's not totally in agreement. Okay, so this is our first paper. We're trying to figure out what happens. But meanwhile, let's just look at, you all know the typhoon track or tropical cyclone track just look like that in East Asia. And and you also all know that Taiwan's here is right in the middle of all this stuff. It's really, really important, even though it's tiny, it's pretty small. Mesoscale feature, 300 kilometers, okay, in climate since 300 kilometers mesoscale, very unimportant. But we also notice that there's a lot of influences in Southeast China and so forth. Of course, it can extend up to Korea and Japan. So here, we go directly to the purpose of this study. Why the model product and the observation are in agreement outside of Asia, but not in agreement in Asia. In Asia, it's confusing because extreme rainfall is contributed by both the monsoon, which in this definition is a local extreme rainfall, and also tropical cyclone. The previous chart says tropical cyclone carry a lot of heavy rainfall. So if you are in Korea, even in Korea, but they say if you're in southern China or in Taiwan, if you want to look at extreme rainfall, you have to know it comes from two sources. Okay, and this every degree of increase of global mean temperature causes 7% increase of water vapor. All this stuff is global, but you could apply the two locally. But if you apply to Asian monsoon region, you have to be careful because the tropical cyclones are coming in from Western North Pacific. So whether tropical cyclone is strong, is weak, has more water vapor, less water vapor, is more energy, less energy, a lot, not all, but a lot depends on where it's generated. So and over the past, before it hits Chinese mainland or Asian mainland or any part of Asia, its property is very much depending on the path, right? It picks up water vapor. It may be weakened by shear or whatever. So when it dumps all this rainfall over Asia, it produces extreme rainfall. But that's not so much related to whether the temperature over this part has increased by 1 degree C over 100 years or not. All right, so therefore, this is somebody visiting from outside, and it's being mixed with the local rainfall. So we need to somehow separate them. And okay, these external factors rather than local thermodynamic conditions. And here the data, I would just say we have good data. That's all we need to say. 53-year-old data. This includes about 500 stations, where most of that is from mainland China, which includes the Hainan Island, and 20 from Taiwan. All right, this is an important point here. We have only daily data. So each day of rainfall, let's say today there's rainfall over Busan, then we have to say whether it's a monsoon rainfall or it's a tropical typhoon TC rainfall, but not both. Okay, we have to classify in that way. And the TC events are identified with this scheme by Ren of China Meteorological Administration. He has divided a scheme in an objective way to determine whether today's Busan rainfall should be called a TC rainfall or monsoon rainfall. Basically, if the TC is within a range of 500 kilometers, then we'll call it TC rainfall regardless. Okay. However, there could be situations where there's remote influences of the TC. We all know that. So he has this technique that's quite smart. He's comparing neighboring stations. So if he can continuously track rainfall of Busan all the way to, say, Taipei, and there's a tropical cyclone in Taipei, or even farther, say Manila, then he call you rainfall here, TC rainfall. That's just his technique. Okay. So we have to do it objectively. Obviously, there are errors, but that's a definition. So influenced by TC, then we assume as a TC rainfall. All right. So here's the result. The total rainfall, the more blue, the darker blue, the more rainfall, the higher values. And so there's very high rainfalls here are millimeter. I think anyhow, this is like amount of rainfall, total rainfall, of which if we have a different here this extreme rainfall distribution, these are different numbers here, 550 to 30. Okay, anything higher than 50 millimeter per day is very dark blue. So this says the total rainfall has this distribution, mostly concentrated in areas that's hit by tropical cyclones, influenced by or monsoon. Monsoon also influenced here. But if you look at extreme rainfall, then it's even more so. Okay, and that's not unexpected. That is expected. And the first chart here shows the percentage of TC rainfall in total rainfall. So over Taiwan here, more than half, or between 1/3 to 1/2 of rainfall is due to tropical cyclone rainfall, but much less here. But there's a lot over the southern coast. But if you only focus on extreme rainfall, then everywhere, mostly everywhere, are because of tropical cyclone, or not because, but 50%, 30%, significant amount of tropical cyclone give you the extreme rainfall. So if you are looking at extreme rainfall over here, then you are really looking mainly at the tropical cyclone contribution rather than the monsoon contribution. Now, linear trend, this is over these 58 years. This is frequency, and that's rainfall intensity, not tropical cyclone intensity, rainfall intensity, how many millimeter per day. And then we see that over this last half century, or actually more than that, 58 years, there's less tropical cyclone coming this way. Okay, there's a decrease in frequency. But intensity-wise, it's more an increase. Okay, the total, of course, is the combination of the two effects. So there are less tropical cyclone coming to this region, but when they come for the southern part of this region, they produce more rainfall. They are more humid. This is a linear trend. Okay, this doesn't include all the up and downs in between. And here we're going to sidestep and just mention one phenomena which Chinese are very concerned about. I don't know whether it concerns other outside of China. Is they call the Naval Beihan, which means the south is flat and north is drought. And this is sort of like a multi-decadal phenomena over the last 50 or could be 80 years, but not longer, that the northern part of this region of northern China gets drier and drier and drier, and the southern China gets more wet and more wet. And in fact, this work was done by Negan and Zhou. They report this work. So the main thing is that there's also a very strong trend over India. It's not just China, but also this part. So for we then divide this region, the China monsoon region, or most of the East Asia monsoon region, but only in the China part, into several subregions. One of the subregions called Northeast China. I'm going to show the subregions a couple of slides later. So Northeast China, here we have 3 lines. They indicate the time series every year, how much rainfall there is. And I think these are extreme rainfall. Okay, this we only look at extreme rainfall, not the total rainfall. And the 3 lines represent these. Remember, we have total rainfall. That's all the rainfall every day. But some days we call TC rainfall. Some days we call monsoon rainfall. So the total is the blue color. That's the total trend. It's downward. The northern drought tendency we just mentioned. But this rainfall, this extreme rainfall, is the combination of monsoon rainfall and tropical cyclone rainfall. And we first determine which days are tropical cyclone, then they give us this trend. And we then subtract that, then we have this other remaining. So we have 3 trends. The total trend is going down, the northern drought, southern flood. But if you look closely, but then the tropical cyclone extreme rainfall is also going down. You take that out, the monsoon rainfall is also going down. However, their slopes are different. How different? You will compare this blue line and this green line. The blue line says this drought situation. In fact, this is extreme rainfall, not total rainfall. So when I say drought, it's not totally correct. But anyhow, extreme rainfall is decreasing. But if you take out the effect of tropical cyclones, then the monsoon rainfall decreasing, but not as fast as the total rainfall. Okay, the total extreme rainfall is decreasing, but the tropical cyclone extreme rainfall is decreasing actually at a larger speed. So the monsoon extreme rainfall is decreasing at a different speed. I think that's the result. I'm going to have numbers next. But first, let's look at southern China. There's not much tropical cyclone in northern China or tropical cyclone rainfall, but in southern China, this is the southeast coast of China. Okay, and the total extreme rainfall actually is increasing, but the tropical cyclone extreme rainfall is not changing very much. So all the increase comes into the monsoon extreme rainfall. So therefore, if you compute the tendency, then even though the 2 lines are parallel, this is a larger tendency, this is a smaller tendency, right? Because you would say this divided by that. But the denominator of this is lower, so the trend is higher. Okay, we look at various regions, northeastern China. There's some, okay, this whole thing is northeast China. Yangtze Valley, this region, and central China, southern China, Taiwan, Hainan. And we just look at northeast China, we just look at southern China. If you look at the total trend, there's an increase of 16.5%. But if you take out the typhoon part, then the green line says increase of 23%. So if you only look at the extreme rainfall trend here, you underestimate, right? You underestimate because even the 2 lines parallel, but remember the trend here means you take this value divided by this value. But this denominator is higher, this denominator is lower, so this trend is higher. So the monsoon rainfall trend is underestimated if you only look at the total, because the tropical cyclone rainfall did not contribute to the increase. And the northern part, even though they show decrease, but if you focus on the monsoon, the decrease is not as large as total. So again, you underestimate. So over all the regions, you underestimate the increasing trend. Okay, remember, we started on this because the model says extreme rainfall should increase, but the observation says it's not obvious. And here it's not obvious because tropical cyclone rainfall was not increasing, actually sometimes decreasing, or not changing. So the monsoon extreme rainfall increase is being masked, covered by this phenomenon. By tropical cyclones not doing its share, it's like tropical cyclones should have increased. Monsoon have increased, then we see the total is increased, but monsoon is not increasing. Tropical cyclone is not increasing, so monsoon is increasing, but it gets dragged down, get underestimated. And in Hainan Island, it's extremely interesting for this period, that this part, look at infinity here, we enlarge the chart here. For Hainan Island, the extreme rainfall is decreasing, but tropical cyclone extreme rainfall is decreasing more. You take out the red, you subtract the red from the blue, you're left with the green. So the monsoon extreme rainfall was increasing, but the total was decreasing. Okay, so therefore, the total shows, okay, over 58 years, extreme rainfall decreased by 15%. But the monsoon actually, extreme rainfall decreased by 35%. The sign is wrong. Okay, this says decrease, but it actually is increased. That's why I don't know any better way. I can't put a number in there. I just put infinity, just told its sign is wrong. It is increasing, but you say it is, you see decrease, but it's increasing. That's the reason is because tropical cyclone has much less frequency and decreased so much. All right. And then we go back to Taiwan. Taiwan is the opposite case. Remember, extreme rainfall keep increasing. We have flood, people die, and government change. In the case of Taiwan, use the same method. If you only look at total extreme rainfall from 58 to 2010, it is increasing a lot. Here this is 1,000, 1,500. This is like 1,200 or 1,250, but there's a very, very, very large increasing. But tropical cyclone trend is even larger, so that the monsoon extreme rainfall trend is lower. And we put numbers in there. The total, if you look at the blue line here, this number divided by that number is about 20. There's 20% increase. But tropical cyclone rainfall increase is more. If this is, it would be 500 divided by 300, it's more than 20%, right? So the monsoon, if you only look at the monsoon extreme rainfall increase, it's only like 10 or 11%. So people are saying, wow, extreme rainfall increased by 20%. But most of that's because of tropical cyclone. So here, the overestimate is 79%. So that means over all these regions, it's underestimate. But in Taiwan, it's overestimate. And the reason is tropical cyclone bringing more extreme rainfall in a large trend, but not so. Actually, in China, it's decreasing. Taiwan, it's increasing and hugely increasing. That, of course, leads to the second part of the talk. This huge increase, is that global warming or not? But first, if you're alert, use your intuition. Global warming effect on tropical cyclone, whether it's intensity, rainfall, whatever, should be on a larger scale. It shouldn't be like this local place is increasing like that, and everybody's global warming. If that's, but everywhere else it's not, then it's unlikely to be global warming. Okay, it's likely to be local effect. But how could the local effect cause such a large increase? Okay, this is a summary. Maybe I'll just read one. Since mid-20th century, decreasing TC rainfall frequency dominate increasing intensity. In most regions, the typhoon extreme rainfall is less than the trend is less than the monsoon extreme rainfall trend. Therefore, the intrinsic monsoon extreme rainfall trend is underestimated. Sign remains mostly, let's see. I think this negative refers to the underestimate. Okay. Don't worry about this. I was taking a side trip to think of a research project to look at a southern flood, northern drought. Northern China is decreasing for its own reason. But anyhow, there's a drastic opposite effect on Hainan, Taiwan. Hainan shows monsoon rainfall is being underestimated, And Taiwan's is the opposite. Large Taiwan extreme rainfall cannot be attributed to thermodynamic effect of global warming because it's localized, it's not large scale. So now if we focus on the Taiwan typhoon rainfall intensity, here we use 21 stations, we just average them all. So Taiwan rainfall has only one number. Even though the 21 stations, we just add them together, okay? I forgot whether we add or we average. And during this period, 1960 to 2011, there were 24 landing typhoons. Only those typhoons actual land Taiwan was used. And okay, here, all these 84 typhoons by the Weather Service have separated them into like 8 or 9 different tracks. And we only look at 3 tracks. The 3 tracks represent maybe about 70% of the total. What 3 tracks? The 3 track here is important for these letters. The 3 track types, north, which means goes north of Taiwan, C means central of Taiwan, south, S means south, and it's easy. I'll use color later. Since north in Taiwan is in north of the equator, so north is cold, so when it's blue, it's north. And when it's red, it's warm, it's south, warm. And C, I'll just use green, okay. And then in addition, there are 3 types and 3 phases. So what 3 phases? Before the typhoon hit Taiwan, it's called pre-landfall phase. While it's over land, it's called overland. And once it moves out, it's called exit phase. Okay, there are PR, OL, and EX. And here we must remember that in Taiwan, typhoon is not over an ocean or a flat land. It has a strong interaction with the terrain. And Taiwan has the highest mountain in northeastern China. I think during lunch, Director Chang mentioned that. You could view the whole Taiwan as this mountain. Taiwan is this one mountain that's come up to give you highest peak in northeastern Asia. It's a big mountain. But Taiwan is small, so we're talking about north-south, 300 kilometers. The mountain, depending on how you define it, could be less, okay? And it's pretty narrow. And when typhoon comes in here, there's strong interaction with terrain, so produce rainfall depending on the interaction. And also, another important thing is there, of course, is an interaction with the monsoon. Here we mean the southwest monsoon because the majority, we're looking actually, typhoon season mostly is during the monsoon region. So that is the background. Okay, here we pick the top 12 rainfall station, rainfall typhoon in top 12, typhoon rainfall. So these 12 typhoons rank number 1 to number 12. And here shows the period they're affecting Taiwan, the total period, which means before and over and after. We're going to have definition what is meant by before and after later. And this is the total rainfall. And this is the one, 2009, that creates the big thing. Okay. And you, up here, there's one typhoon, 2001. This affects Taiwan for more than 3 days. This is a special one. We have to exclude it. It goes like a north to south. It's weird. Okay. It goes around Taiwan and goes north, enter Taipei and coming out of the southern tail and just wandering around and so forth. So, of course, when it stays so long, it rains a lot, total rainfall. So we highlight all those that's after 2004. So most of them are after 2004. When we add 3 or 4 more years, then we push this out, another typhoon come in. That was recent, also after 2004. So this shows all these typhoons that recent typhoons produce large rainfall. All right, here, this is that mountain, central mountain range, I guess called CMR. It's narrow, it's very high around here, and that is not quite 200 kilometers, very narrow. And those are the stations. Okay, the 3 tracks. The blue color are all those typhoons in the north track. They always go from here to here. Okay, southeast to northwest. That's the northern track. All the central tracks are plotted here, and all the southern tracks are plotted here. And if These are just examples. They're not composite. This one typhoon, 2006 Kameji, at 925 millibar, it is they're streamlined, and when the center is north. And this is 2009. That is big typhoon Moraka. Is of the central type, and this is an example of the southern type. And remember, because of mountains, so the interactions are not symmetric. So over here, if a typhoon is to the north in the northern track, then on this side, there's more interaction, maxima terrain interaction. If it's on the south side, then the terrain interaction is minimum. If it's the central side, central track, then this is in between. However, monsoon comes out this way from, right? This is the direction of the southwest monsoon. So the central track has the intermediate interaction with the terrain because of the flow interface with the mountain, but it has the maxima southwest monsoon. The northern one is too far from southwest. The southern one it's southwest, the center itself is too far to the south. So the central one would have more interaction. And here, what is mean by before landing, over landing, and after landing? We just take 100 kilometers from any point, measure 100 kilometers. So if a track comes out this way, when it's 100 kilometers from the coastal area, we call that pre-land phase, PL phase. This is the overland, and this is exit when it's 100 kilometers. It's 100 kilometers all directions of the coast, but this envelope is not Taiwan. Okay, turns out that you don't have a Taiwan envelope. It's going to look like this. All right, let's look at the pre-landing. Here, all these typhoons are coming in within 100 kilometers of the east coast of Taiwan. There are all these typhoons we plotted here. Some are duplicate. What is this chart? This is duration versus rainfall amount. The longer the typhoon affects or influences Taiwan over this PR, before it comes in within 100 kilometers, the longer the time, there should be more rainfall, right? So if every typhoon in this, before they hit the Taiwan, has the same intensity, then all these dots are going to line up on this line. And so we need a number to measure whether they're all lined up or scattered. And this will be, you just do a regression or curve fitting and take this R square, which is called coefficient of determination, which is called R square. When it's all scattered, R square is small. When it's all lined up, R square is 1. Okay? So here this says so these various typhoons do not have the same intensity. They are scattered all over. Why? Because they're all over, because its number is small. But if you focus on the northern track, which means the others are now in gray, only the blue ones, even this one, has a lot of rainfall. But why does it have a lot of rainfall? Because it's been there a longer time. Duration is longer. So here the R square is 0.64. That means they are more clustered. That means there is not that huge a variation in the intensity. Say, if everybody line up in a line, then you cannot say climate change. Why do you have more rainfall? Why do you have flood? Because the typhoon's been there staying for a longer duration, so it rains more. Okay? Well, you could say there's climate change in the movement, but not climate change in the intensity when they all fit together. So if you look at everything, then the R square is small. They're scattered. There's maybe changes. But you focus on track base, then the number is not small, it's large. If you focus only on the central typhoons, central track, they all line up in this line, so you got a large R square. So there's not much variation from 50 years ago or 30 years ago to now in terms of intensity. There may be variation in duration, but not intensity, because when the intensity is defined as rainfall amount divided by the duration. If you look at the southern track, R square is a bit small, but still higher than when you put all total together. So we put all total together, then say If you look at all of them together, then you see these large intensity changes because R squared is small. But if you focus on each track, north, central, and south, then north and central are not small, and even south is better than these. Let's see. Okay, so the first lesson we learned is that maybe there's no intensity increase, but typhoon just moved to, there are more typhoons coming in from north than from in south. Okay, that is the important message. And since Taiwan is so small, the mountain, we're talking about difference of 100 kilometers between the tracks. So it is hard to argue that global warming caused some track changes cause this, because it's so small, it's mesoscale change. And more interesting is this chart where, let's look at this, whether it's scattered or not scattered, the rainfall over the years versus duration. I need to explain this. 6 hours, what does 6 hours mean? This means when the typhoon enters our region, 100 kilometers from the coast, we start a timer, start the clock. So the first 6 hours, the coefficient of determination is very small, whether it's the north track, central track, south track, or all total. They're small numbers. That means they're scattered all over. Then you go on for 9 hours, they're even smaller. Go to 12 hours, they become large. And if you go to the entire course, they become larger, except the black line, that's total. So this means as typhoons approaches Taiwan, the rainfall intensity initially are scattered. But once they move real close to the land, then they are not scattered anymore. Not scattered means the intensity are similar when it's not scattered. So this gives us first hint, namely the terrain influence, the mountain influence, has a lot of influence. So when typhoons are being influenced by mountain, their intensity do not differ too much from one another. That is the important point. Okay, this typhoon has heavy, intense rainfall. That typhoon has less intense rainfall. But when they approach Taiwan, their intensity becomes similar because the scattering is smaller. They fit in the curve. And they are all over 0.6. And if we look at the actual rainfall, then there's more rainfall in north track, less in central, and even less in south, just because of the terrain interaction. Now, what if typhoons over land? Then that's what the chart looks like. Over land, everybody has high numbers, 0.85, 0.66, 0.73. And if you put all together, they fit nicely 0.74. So what does that mean? This means as the typhoon is over Taiwan, their rainfall intensity do not change much. It confirms what I said earlier. Namely, the mountain decides the rainfall intensity. You may come in with so much water vapor, you will rain like hell, and create very large rainfall in a short time. Or another one doesn't have that much rainfall. But when everybody come to Taiwan, then the rainfall intensity are similar. Whether you have more rainfall or less rainfall depends on whether you stay here longer or shorter. Duration determines, but intensity is similar. So the mountain exerts a strong control on the rainfall intensity. Again, rainfall intensity is not a total, it's the speed of rainfall. Okay, so the mountain has a strong control over that. Now, if you have a similar chart, then from the time the typhoon enters over land, then these numbers are all high. Okay, it's organized. This means they're organized to have similar intensities. And over land, you have more rainfall for the north track because mountain interaction is stronger, and central is also more, and south track is not so much impact by the mountains, so that's smaller. Now, as the typhoon goes out, the northern one, the central one, all have higher coefficient, 0.55. The southern one, but they're lower than before, and the total is low. And this is expected because tropical cyclones have left Taiwan, so the mountain influence is smaller. So they began to scatter. But if you follow each track, they're not as scattered as if you lump them together. And if we have a similar chart, then they never, once they leave, they cannot reach above 0.6. So if we put this chart together, this says northern tract has more rainfall here before hitting land, over land. Also high rainfall exit, but not as much as before. Central tract has the second largest rainfall before hitting land, over land. But by the time the central tract cyclones leaves Taiwan, it actually has a bit more rainfall than that, and this is comparable. And the reason we explain that is because both the terrain interaction and the monsoon interaction are in effect. So because it reduces the monsoon interaction. And the southern one, it does not interact with the terrain so much, so it gives less rainfall. All right, so the conclusion at this point is that tropical cyclone intensity hitting Taiwan did not vary that much if you look at tracks. If you only look at north tracks, only look at central tracks, only look at south tracks, then they don't vary as much as if you don't look at track. Put everything together, then you see, the rainfall is more intense lately than 10 years ago. And since after 2004, this horizontal coordinate is year 1960 to 2012. We have extended to 2013. This 2004, the rainfall intensity is higher after 2004 and less. So we put every cases of the three tracks in this chart. And then we go in and count how many typhoons of which track before 2004 and after 2004. And we also look at the duration. And we came out with this. The upper panel is the frequency of tropical cyclone during the earlier period. That's 44 years. And here, this is only 8 years. So the 44 years, these are number of typhoons hitting Taiwan, north, central, and south. I should blue color this. And lately, the most recent 8 years, these are the numbers. And these are the duration. And the percentage here are relative, namely out of all these typhoons, what's the percentage of north, what's the percentage of central, percentage of south. And first, we can notice there are more typhoons, more frequency, because say over 44 years you have 21. But here over 8 years you have 5. Say 44, 21, that's like half of that, right? Less than half. 44 you should have 22. But 8 you should have 4. So there's a bit less, a bit more. But relative frequency wise, the northern typhoon reduced by how much? By about 1/3. Okay, 45, you take 1/3 out of 30. So frequency reduced by 1/3. This is relative frequency, not total total frequency increase, but compared to frequencies of other tracks, it reduced by 1/3. But the duration is increased by 50% from 16 to 24. That's increased by 50%. So this means between the earlier period and most recent period, northern track relatively is less, but it stays longer. When that happens, it's going to rain more. Central track, relative frequency jumps from 32 to 50, and the duration is the same. So central track typhoons over Taiwan stay about the same number of hours, 24 hours. But there are more central ones. And southern track, there are less. And their duration is similar, but they come in less. So if we just summarize in a very simple way, is that if you compare the first 44 years with the later 8 years, you can make the following statement, saying there's a track shift. There are more typhoons coming from the north and the central than from the south. And furthermore, especially more around central track. And furthermore, for the northern tracks, it rains a lot. Okay, so this is the conclusion at this point. Here, relative frequency reduced by 1/3, increased by 2/3, and But the reduced by 1/3 thing is increased by half in terms of duration. It stays longer. Just when it stays longer, it rains more. And we're trying to see whether we can find some literature to explain these track changes. You may have all read about Pacific typhoon tropical cyclone track changes, that during this later period, there are more tropical cyclones coming this way, Japan, Korea, than going west towards Hainan and southern China. And that explains why there's just less. However, that track separation is pretty large. And here we're talking about 100 kilometers. And further, you really cannot say that work is related to this, because we're talking about 100 kilometers. And furthermore, I think in this Taiwan, it is belongs to the South track. Both the North and Southern Taiwan are one type. They're not like the two. Okay, but there's another work which shows that there's a slowing down of the steering flow of tropical cyclone steering flow over Western North Pacific. And so this work basically says that in the latitude of around 20 north, the steering flow in NSAT analysis is slower. If the steering flow is slower, then typhoons move slower. When typhoons move slower, then they have longer duration. They would have more rainfall, and that would correspond to the northern track. They used to stay 16 hours, now they stay 24 hours. So that may be used to explain why it rains more, because it stays longer. And the southern ones do not stay longer. They're just a little bit south, perhaps, from what the steering flow calculated. But I have more to say on this later. So back to the table of the 12 most rainfall typhoons. There are additional information showing this a longer or shorter duration. And here the track type. We notice all of these track types are north or central, and there's no south. And there's some special and other track type. So only the northern and the central tracks produce more rainfall. And the northern track produced more rainfall lately, and central track, even though it did not produce more rainfall, there are more central track coming. So we're explaining Taiwan's larger rainfall by the following. Number one, more northern track rainfall and rains a lot more. Number two, even more central track. Okay, and a lot more because it stayed there longer. And southern tracks are actually less. So if you have this situation, you're going to have more rainfall. So that explanation is very local. It's not answering the question of global warming. And it cannot answer. In fact, it says you don't need global warming. It implies it's not related to global warming. But in the mind of many, not only news media and government officials, in the mind of people, including my colleagues, professors, scientists, and they say, look, our extreme rainfall increased so much, and that's our global warming, we got to do something about it. Okay, I'm not saying we shouldn't do anything about it. We're just saying the relationships, they got confused. So you have to look closer. And if you really want to, okay, I'm going to skip those charts. If you really want to look at whether there's climate change, because climate change could cause some local changes. And this is to look at decadal change from 1960 to 2012. We have three phases of the rainfall intensity. So if you look at the before hitting land, that's the blue one, and we do not see an increasing trend. Over land is the black one. I don't know whether you see or not see, and I do not see increasing trend. And red is when the tropical cyclone leave Taiwan, going to Taiwan Strait, or hitting mainland China, then I would say there's an increasing trend. So this is this does not mean typhoon leaving Taiwan rains more there. We're all talking about Taiwan rainfall. Typhoon has left, but Taiwan still rain. Okay, we're only looking at Taiwan rainfall. But they call this rainfall associated with a typhoon. And if you just average the period here and here, those are the numbers. There is no increase, no apparent increase for the typhoon before they hit Taiwan, when they hit Taiwan, but there's increase after they hit Taiwan. Okay, that's the rainfall intensity. So yes, rainfall intensity indeed increases over this period from the first 26 years to the late, there's decadal increase in trend, but that increase in trend is limited to when the typhoon leaves Taiwan. So then we scratch our head, say, what does that mean? Our guess is southwest monsoon, because before the typhoon hit Taiwan, it is not interacting with the southwest monsoon. Overland interacts somewhat, but mainly when it leaves, then interact a lot more. So therefore, the increase in rainfall is associated with southwest monsoon. So there's a climate change in there. There's an increasing trend of southwest monsoon that causes this increasing of Taiwan rainfall, but it only occurs when the typhoon leaves Taiwan. Okay, I hope that's not too confusing. Okay, some people say this global warming feedback thing gives you stronger typhoons. So that excludes stronger typhoons. So over here, we produce the same chart, but we put the category 4 to 5 typhoons in there. And you will see there are more category 4 to 5 here than here. And the results are similar. No change, not much change, large change. So the same conclusion applies. So the increasing of rainfall is not due to more stronger typhoons. It is not due to something before typhoon hits Taiwan or when Taiwan, but it's afterward. Therefore, it's likely the southwest monsoon. Okay, so southwest monsoon has increased. And then we go to Professor Bing Wang's work. You probably all seen this before. In fact, we can just summarize in a very one-sentence statement. This work basically says the northern hemisphere tropical monsoon has increased over this period. If you think the northern, his monsoon is not East Asian monsoon. His monsoon is 20 north. Okay, so he's saying over this period, the monsoon between 10 and 20 north has increased, and that is useful to us. Because we're saying the Taiwan has more rainfall after the typhoon interact with the southwest monsoon. And if the southwest monsoon increases, then the rainfall increases. So this is where if we have to find some explanation, we'll go that way. Meanwhile, why is the rainfall even before typhoon hit Taiwan or over? It's because typhoon has stayed there longer. The northern track stays there longer. Instead of 16 hours, say 24 hours, it rain like hell. Now, why it stays longer? Because steering flow is slower. Why is steering flow slower? If you think the westerly wind is stronger, then the easterly wind is slower. So you could piece together. This is all, I would say, somewhat a speculation. But it's self-consistent. If you think Professor Bing Wang's work showing this tropical southwest monsoon has slowed down, tropical, not mid-latitude, then that would agree with the slowing down of the steering flow at this latitude. Therefore, the northern and central track typhoon, especially the northern typhoon, when they hit Taiwan, before they hit, over they hit, they're going to move slower, they rain more. That's a very simple reason. It's not because temperatures higher, more water vapor, because they move slower, they rain more. But once they exit Taiwan, then they have more true increase in rainfall intensity. They move at the same speed, same duration, more rain. That's a true increase in intensity. And that true increase in intensity has to do with this stronger interaction with the southwest monsoon. And that, again, is consistent with the first part that it moves slower. So then they further say, why is the monsoon weaker? tropical monsoon. Because if you go to the global warming theory, then the theory says that tropical circulation, let's say, or the worker circulation will be slowed down. It will be slowed down because when you increase temperature, you increase too much water vapor. And water vapor cannot, then you offset radiation, but you're something like that. So tropical motion have to slow down. And in this case, the west wind is not slowing down, but speeding up. So there's another sort of evidence indirectly that this cannot be explained by global warming. And they did further work, I think, if I can. Oh, this is another, I have some extra. I think they showed that this increasing of tropical southwestern monsoon have better agreement with AMO and PDO, the Pacific Decadal and the Atlantic multi-decadal oscillation. And they are natural variations. They are considered natural variations, although there's controversy on that as well. And then they also agree with this north-south temperature series, which would be like global warming. But if you listen to him, then he thinks these are less likely to be due to global warming, the direction. So we have weak, not strong, weak evidence that global warming would not give you this conclusion. If I am brave, if I'm brave, I'm really brave, then I could go out saying global warming would cause Taiwan to have less rainfall. This is the opposite to that is. Okay, this is as far as we can go. We can't really push the envelope any further. But really it convinced me that most of the increased rainfall, apparent increase of extreme rainfall in Taiwan are not related to global warming. Okay, I think when you put weak evidence together, and they're all consistent, they're not like one is conflict. Consistent weak evidence together, then your strength of the evidence is a bit higher. Right? So that's all my talk.